In this video, we're going to do another variational problem, which is the hydrogen molecule ion. We'll first identify the trial function for this problem. Then we'll arrange the coordinate systems to make the integrals possible. We'll normalize the wave function, calculate the direct and exchange integrals, and then finally compute the final energy and bond length. The Hamiltonian for the hydrogen molecule ion has 2 protons and 1 electron. The vectors between the electron and the individual protons are labeled as R1 and R2. The Hamiltonian then is minus h bar squared over 2m times the Laplacian minus the potential, which is E squared over 4 pi epsilon naught times the quantity 1 over R1 plus 1 over R2. The trial solution we're going to use is a linear combination of atomic orbitals centered about each of the protons. That is, psi is equal to A, the normalization constant, times the ground state of the hydrogen atom about proton 1 plus the ground state of the hydrogen atom about proton 2. This is equal to the normalization constant divided by the square root of pi a cubed times the quantity e to the minus r1 over a plus e to the minus r2 over a. We have to normalize this to get our normalization constant before we can do anything else. And the normalization integral is 1 is equal to psi squared d cubed r, integrated over all space. And this gives us 3 different integrals. So we have the first integral is simply the normalization of the hydrogen wave function, the hydrogen ground state, around the proton 1. The second one is the same thing around proton 2. And the third integral is 2 times an overlap integral of psi 0 about r1 times psi 0 about r2 d cubed r. Well, the first 2 just give you 1. And the third one gives you 2 times this integral here, which we call the overlap integral. And we'll label that I. So we need to remember this because we're going to calculate I and then come back and calculate A squared. So I, once you substitute in the wave functions, is equal to 1 over pi a cubed times the integral of e to the minus r1 plus r2 over a times r squared sine theta dr d theta d phi. The ideal coordinate system for this integral is to put proton 1 at the origin. That way, the coordinate r is identical to the coordinate r1. And the orientation of the z-axis should be along the distance from proton 1 to proton 2, where proton 2 is a distance capital R from proton 1. That makes this triangle here, which we can use to calculate the value of R2. So R1 is simply equal to R. But R2 can be written now in terms of this triangle as the square root of R squared plus capital R squared minus 2R capital R cosine theta. If we do the phi integration, since there's no phi dependence anywhere, we get 2 pi. And so our overlap integral then looks like 2 pi over pi a cubed, integral from 0 to infinity over r, integral from 0 to pi over theta, e to the minus r over a, times e to the minus square root of r squared plus capital R squared minus 2r capital R cosine theta over a, r squared sine theta dr d theta. We'll first look at the theta integral, which means we can ignore this term here, this first exponential. We can ignore this r squared, and we can ignore the dr. And we'll now just keep the theta components. So the theta integral is just the integral from 0 to pi of e to the minus square root of r squared plus capital R squared minus 2r capital R cosine theta over a times the sine theta d theta. We can make this a lot simpler by doing a simple substitution. We'll take everything under the square root and call it y. If we square that and take the full derivative of that, of y squared, we get the the derivative of y squared is 2y dy. And since the only thing we care about here is the theta integral, not the r integral, when we take y squared and take the derivative with respect to theta, we only have one term. And that term cancels the minus sign because the derivative of cosine is minus sine. And we get that's equal to 2r, capital R, sine theta d theta. So that goes into the place of sine theta d theta. When we do this substitution, we simplify this to get 1 over r capital R, integral from absolute value of r minus capital R to r plus r, y e to the minus y over a dy. This can be done by integration by parts. So the first integration by parts gives you 1 over r capital R minus ay e to the minus y over a, evaluated at the two limits, plus the integral of a times the integral of e to the minus y over a dy, evaluated at the two limits. Well, this first term gives us two pieces. So you have a over r capital R times the quantity minus r plus capital R e to the minus r plus capital R over a, plus the absolute value of r minus capital R e to the minus absolute value of r minus capital R over a. And then this integral here gives us also two terms. The first one is minus a e to the minus r plus capital R over a, and the second one is plus a e to the minus absolute value of r minus capital R over a. So we can now do a little bit of consolidation. We have terms with two different exponential functions. So we have minus a over r capital R times the quantity r plus capital R plus a times e to the minus r plus capital R over a, minus the quantity absolute value of r minus capital R plus a, times e to the minus absolute value of r minus capital R over a. Therefore, we get, for the overlap integral, substituting the result of the theta integral back into the overlap integral, we get minus 2 over capital R a squared, integral from 0 to infinity over r, of r times this quantity here in the brackets, which is exactly what we got from the theta integral, times e to the minus r over a dr. And that's where we are. So this integral now has to be done as a bunch of integration by parts. We have this term up here, which is e to the minus r plus capital R over a. Then we have an r squared, and then we have r capital R, and then we have plus ra, and we have three terms there. And similarly, we can bring the r into here as well. And we can also bring e to the minus ra in. So when we combine these, we get the following, several integrals. We can first take out the e to the minus capital R over a. That factors out. Then we have an integral from 0 to infinity of r squared plus r times r capital R plus a, e to the minus 2r over a. That's from this term here and this term here, with the factored out term here. We then get a second term, which is e to the minus e to the minus r over a. And then you have, when you have this term here, times the r here. So when little r, when the variable is less than capital R, this just becomes capital R minus a. And so you're left with an integral from 0 to capital R of r times capital R plus a minus r squared dr. And then you get a second term, when r is bigger than capital R, so you get the integral from r, capital R to infinity of e to the minus capital R over a times r squared minus r times r, capital R minus a, e to the minus 2r over a dr. So in one case, you get a cancellation of the exponentials, that's the one in blue. And the other case, you get the exponentials combined to give you e to the minus 2r over a. And then you have the first term, which is much more straightforward. Well, I can do this also, this red integral, I can do by integration by parts. And when I do that, I get the following integral at the end. The result is e to the minus capital R over a times the quantity minus 2a cubed over 8 minus a squared over 4 times r, capital R times a, e to the minus 2r over a evaluated from 0 to infinity. In the blue integral, again we have the limits are 0 to capital R, and we can do this again by integration by parts, the appropriate number of times, twice here and once here. And you get minus e to the minus capital R over a times r squared over 2 times capital R plus a minus r cubed over 3 evaluated from 0 to capital R. And then you have this final term here, which again, you can do by integration by parts. And this gives you a few terms. So it's e to the minus capital R over a times a over 2r squared minus 2a squared over 4r minus 2a cubed over 8 plus 2a over 2r times capital R minus a plus a squared over 4 times capital R minus a times e to the minus 2r over a evaluated from capital R to infinity. So looking at the limits here, when r goes to infinity, this term goes to 0 and cancels everything out. And at 0, this evaluates to 1. And so we're left with these terms here. In this case here, you get when lowercase r is equal to capital R, you get a value, which is capital R squared over 2 times capital R plus a minus capital R cubed over 3. And when it's 0, all these terms cancel. So you only get one of the two limits. And then in this case, in the green case, again, the infinity knocks everything out because this term goes to 0. And at r, all these terms survive, and you're left with e to the minus 2 capital R over a times e to the capital R over a, which will combine. And then all these terms in here with the capital R's instead of the lowercase r's. And we can write that down then by pulling out first our common terms, which are minus 2 over capital R a squared e to the minus capital R over a. It's a common term for this, common term for this, and a common term for this once you drop in the capital R here and you multiply this out. From the red integral, in the red terms, you get a cubed over 4 plus a squared capital R over 4 plus a cubed over 4. From the blue terms, you get minus capital R cubed over 2 minus a capital R squared over 2 plus capital R cubed over 3. And from the green terms, you get minus a capital R squared over 2 plus a squared capital R over 2 minus a cubed over 4 plus a capital R squared over 2 minus a squared capital R over 2 plus a squared capital R over 4 minus a cubed over 4. When you gather all these terms, it's a long integral, you get that the integral I is equal to 2 over r, capital R a squared e to the minus capital R over a squared capital R over 2, plus a capital R squared over 2, plus r cubed, capital R cubed over 6. And that's the final value of this integral. We now have to put this back into the normalization equation. we can simplify it just a little bit more by pulling these terms into the brackets. We get e to the minus capital R over A times 1 plus capital R over A plus 1/3 capital R over A squared. So a rather simple solution at the end. Now remember, the normalization constant is expressed in terms of the overlap integral as follows. A squared is equal to 1 over 2 times 1 plus I, this being I. And we'll leave it like that for the moment. Now we want to calculate the expectation value of the Hamiltonian to use the variational method. Remember, the Hamiltonian applied to psi is equal to minus h bar squared over 2m times the Laplacian minus e squared over 4 pi epsilon naught times 1 over r1 plus 1 over r2 applied to the wave function, which is a, which is defined by this expression here, times psi 0 of r1 plus psi 0 of r2. Well, this gives us several terms. The first term, when you apply the Laplacian to the first term here, you get minus h bar squared over 2m, Laplacian of a psi 0 of r1, minus h bar squared over 2m times the Laplacian of a applied to a psi 0 of r2, minus a times e squared over 4 pi epsilon naught. And now we have four terms here, 1 over r1 times psi 0 of r1, plus 1 over r1 times psi 0 of r2, plus 1 over r2 times psi 0 of r1, plus 1 over r2 times psi 0 of r2. So you can see a pattern here. Here the two variables match, here they mismatch. Here they mismatch, and here they match, R2s in both cases. We can now grab the ones in red and the ones in blue and group them together. So this term in red and this term in red are merely the Hamiltonian for the hydrogen atom when the electron is attracted to proton 1. And the blue ones are the same thing for when the electron is attracted to the proton 2. And so we know what the value is there because the hydrogen atom will give you the ground state energy. And so we have A times E1, the ground state energy of the hydrogen atom, times psi 0 of R1 back again, plus A times E1 times psi 0 of R2 back again. And what's left are these two terms here, which we don't know right now. We'll have to do an integral. And these are minus A times E squared over 4 pi epsilon naught times the quantity 1 over R1 psi 0 of R2 plus 1 over R2 psi 0 of R1. In order to get the expectation value, because that's what we do for the variational method, we have to take an inner product. And we'll take the inner product with our trial function on the other side. So on the left side we have the trial function, on the right side we have h applied to the trial function. So we have the expectation value of the Hamiltonian is a squared, which is defined by that overlap integral, times the inner product of psi 0 r1 plus psi 0 r2 with E1 times psi 0 r1 plus psi 0 r2 minus E squared over 4 pi epsilon naught 1 over r1 psi 0 of r2 plus 1 over r2 psi 0 of r1. Now this first term is simple. You just get E1. But then you have these two integrals that are left over. So the second term, as I mentioned, produces four terms which can be grouped into two different types of integrals. So you have psi 0 of r1 and then psi 0 of r2, psi 0 of r1 and psi 0 of r1, psi 0 of r2 and psi 0 of r2, and psi 0 of r2 and psi 0 of r1, with the various potentials here. We can write that now in the following way. The expectation value of the Hamiltonian is E1 from this first term minus 2 times absolute value of a squared over e times e squared over 4 pi epsilon naught times the quantity of two inner products. The first one looks like psi 0 of R2, 1 over R1, psi 0 of R2. So on this one, both the variables on either side are the same, and the function in the middle is the different variable. So R2 here and 1 over R1. That's clearly this term and this term. But it also represents this term times this term, except you replace R1 with R2. And so we just say those integrals are going to be identical because the electron doesn't really care whether it's talking about R1 and R2 because there's a symmetry there. And so you get 2 times that integral. The second integral is when you have psi 0 of R1, 1 over R1, and then psi 0 of R2 on the other side. So there's 2 of those also. Again, you can swap the R1s and R2s and get exactly those 2. The first one is called the direct integral because you have the same wave function on both sides and a potential that depends on a different variable. And that's given as A times psi 0 of R2 times 1 over R1 times psi 0 over R2, all integrated together. The second one is called an exchange integral. And we're writing this as x is equal to A times the inner product of psi 0 of R1, 1 over R1, psi 0 of R2. So you can see what this is. This is sort of the electron wave function around one proton and the potential that's due to the other proton. And here you have the exchange integral where you're changing from one proton to the other proton and the overlap between those two with the potential from the first proton. Now when you do those integrals, which are done in problem 8.9, they become relatively simple after quite a lot of work. The direct integral becomes A over capital R minus the quantity 1 minus A over capital R e to the minus 2 capital R over A. And the exchange integral is e to the minus 2 over A times the quantity 1 plus capital R over A. So now we can calculate the full expectation value of the Hamiltonian. We recall that the normalization constant, capital A squared, is equal to 1/2 times 1 over 1 plus the overlap integral I, where the overlap integral I is e to the minus capital R over A times the quantity 1 plus R over A plus 1/3 R over A squared. And so we can now write everything together. We say that the Hamiltonian is the energy of a hydrogen atom, right? Because that's the energy of the electron around one of the two protons. We don't care which one it is. Minus 2 times the normalization constant squared times E squared over 4 pi epsilon naught times the quantity direct integral over A plus x over A. If we now put in the value for A squared, we get that this is equal to 1 plus 2 times the direct plus the exchange integral divided by 1 plus the overlap integral I, all times E1. Now there's one more thing we have to include here, and that's the proton-proton repulsion energy, because you have two positive charges, they will repel. But this is constant for the electronic wave functions, because protons move much more slowly because they're 2,000 times more massive than the electron. So we're going to assume it's a constant value, but we can allow that to vary in our variational method to minimize the total energy. Well, that proton energy we'll call V sub pp is E squared over 4 pi epsilon naught times 1 over capital R. And this is simply minus 2a over r, capital R, times the energy of the hydrogen atom, the ground state. So we now put it all together. It becomes something rather complicated. It becomes this whole big thing in brackets, which is 1 plus 2 times a over r minus 1 plus a over r e to the minus 2r over a, plus 1 plus r over a e to the minus 2r over a, all over 1 plus e to the minus 2r over a times the quantity 1 plus r over a plus 1/3 r over a squared. Everything minus 2a over r, capital R, times E1, all times E1. If we now make a simple substitution of x is equal to r over a, we get a function f of x, which is the expectation value of h over minus E1, becomes minus 1 plus 2 over x times the quantity 1 minus 2/3 x squared e to the minus x plus 1 plus x e to the minus 2x, all over 1 plus the quantity 1 plus x plus 1/3 x squared, all times e to the minus x. We can plot this. It's a hard one to minimize, but we can plot it. We can find the minimum. And the minimum is when you minimize, when you change r to get the minimum value. But r is directly related to x. So if you minimize this versus x, you'll find the minimum value and the equilibrium position of the two protons. So you can see that f of x versus x goes to a very large value when x gets small. That is, when the two protons become very close. It's dominated, the energy is dominated by the proton-proton repulsion. And then when it goes to infinity, it looks like E1. It approaches E1, which makes sense because as you go far away, the electron will either be around one of the protons or the other proton, and it'll look just like a hydrogen atom. And in the middle, since this drops down rapidly, like 1 over r, and this goes to E1 at infinity, you get a minimum. And the minimum appears at the equilibrium distance. So R equilibrium is equal to 2.4 times the Bohr radius, which is about 1.3 angstroms. The binding energy, the energy below E1, so the difference between E1 and the bottom of this curve, is 1.8 electron volts. So you lower the energy by 1.8 electron volts from the energy of a hydrogen atom by having the second proton there. Experimentally, this is not quite right. So this simple model gives us something that is close, but it's off by 0.24 angstroms, and it's off by about 1 electron volt. But the idea is clear. This becomes a stable molecule with the electron being shared by between the two protons. At this equilibrium distance, the electron is equally shared by the two protons and forms a bond between the two protons, holding everything together with a lowered energy compared to the case where you have the protons flying apart and one carrying the electron away with it.